അതിനകത്ത് ഒരു വീതം കിട്ടും, ഒരു വീതം
ഒരു വീതം ബാക്കി എടുത്ത് വരണം.
മറ്റേ 2 വീതം രണ്ടും കൂടെ ഒന്നിച്ച്
അതെ
പറവുകാരുടെ 3 വീതം ഒന്നിച്ച്.
അതല്ല ഞാൻ പറഞ്ഞേ, ഈ ഒന്ന് അമ്മയുടെ ഒന്ന് മച്ചന്മാന്റെ ബാക്കി 9 വീതം ഒറ്റ പീസാണ്. ഒറ്റ പീസാണ് വിറ്റ് കഴിഞ്ഞാൽ ആ വിറ്റ പൈസ 9 ആയിട്ട് വിരിക്കുക. പിന്നെ എന്താ
അതല്ല 20,000 സെന്റിനേ ഉള്ളൂ എന്ന് പറഞ്ഞാൽ നമ്മൾ തയ്ക്കേണ്ടതാണ്.
വെള്ളരിക്കപ്പെട്ടതിൽ പറഞ്ഞ പോലെ അങ്ങനെ പറയൂ അമ്മേ. അമ്മ അവിടെ ഇപ്പോൾ 1.5 രൂപ വിലയുണ്ടെങ്കിൽ കൂടി വന്നാൽ ചിലപ്പോൾ അങ്ങോട്ടും ഇങ്ങോട്ടും 14-20 മാറ്റം കിട്ടും. ഇപ്പോൾ 1.40 കിട്ടുള്ളൂ, അല്ലെങ്കിൽ 1.60 കിട്ടി ഭാഗ്യത്തിന്, അങ്ങനെയൊക്കെ അവിടെ വേരിയേഷൻ വരുള്ളൂ. അല്ലാണ്ട് 1.5 രൂപയുടെ സ്ഥലത്ത് നാളെ വന്നിട്ട് ഞാൻ പറയുവാണ് 14 രൂപ ആള് വന്നിട്ടുള്ളൂ, അങ്ങനെ വിളിച്ച് പറയുമായിരിക്കും, അങ്ങനെ വിളിച്ച് പറയുമായിരിക്കും. പിന്നെ അമ്മ പറഞ്ഞില്ലേ 2 ലക്ഷം രൂപ പോയി, അത് ചെറിയ കൊടുക്കാൻ പോകും 5 സെന്റ് അല്ലെങ്കിൽ മാക്സിമം 10 സെന്റ്. അവിടുത്തെ ആക്ച്വൽ വില. പക്ഷെ എനിക്ക് തോന്നുന്നത് 1 രൂപ 2 രൂപയുടെ ഉള്ളിലുള്ള കളിയുള്ളൂ അവിടെ എന്ന് എനിക്ക് തോന്നുന്നു. കാരണം അതിന് വേണ്ടുന്നാലും എനിക്ക് തോന്നുന്നത് പ്രത്യേകിച്ച് 70 സെന്റിലൂടെ എനിക്കറിയില്ല കേട്ടോ എത്രയാ എനിക്ക് പോയേക്കാന്ന്. അവിടെ വലിയ പബ്ലിക് കച്ചവടത്തിൽ എത്ര രൂപ പോയേക്കെന്ന് അന്വേഷിച്ച് നോക്കി അറിയാമല്ലോ. 2 രൂപ ചെറിയ പ്ലോട്ടാണ്. ചെറിയ പ്ലോട്ട് കിട്ടും 2 രൂപ, 5 സെന്റ് 6 സെന്റ് 7 സെന്റ് ഒക്കെ ആണെങ്കിൽ 2 രൂപ കിട്ടും. ഈ
ചെറിയ പ്ലോട്ടാണെങ്കിൽ 3 രൂപ 4 രൂപ.
ഇത്രയും വലിയ പ്ലോട്ടിന് അവിടെ എന്താ പറയുക, അവിടെ തൊട്ടടുത്തുള്ള ആൾക്കാരോട് ചോദിച്ചു കഴിഞ്ഞാൽ അറിയാൻ പറ്റും. അന്നേ അത് ഈ പറഞ്ഞ വിലക്ക് കച്ചവടമായി പോകുന്നതായിരുന്നു. കറക്റ്റ് 10 ലക്ഷം അന്ന് കിട്ടുകയും ചെയ്യുമായിരുന്നു. അന്നെല്ലാം പിരിഞ്ഞ് പോയാലും പറഞ്ഞു എന്നാണ് അന്ന് പറഞ്ഞതാണ്. ഒരു 2 കൊല്ലം 2 കൊല്ലം മുമ്പുള്ള രണ്ടൊന്നുമല്ല, അതിന് 3 കൊല്ലം മുമ്പത്തെ കാര്യമാണ്. ഇപ്പൊ അവർക്ക് നാട്ടിലൊന്നും ഇല്ലാത്ത വില വേണമെന്നാണ് പറഞ്ഞത്. ഒരു 2 ലക്ഷം രൂപ 3 ലക്ഷം രൂപ സെന്റിന് വില വന്നാലേ വിൽക്കുള്ളൂ എന്നുള്ള രീതിയിലാണോ പറയണേ? ഈ അമ്മയോട്ടും കാര്യം പറ, ലക്ഷമാനോ പോവാനും മുന്നേ പരിപാടി നടക്കാൻ പറ, അല്ലെങ്കിൽ അതിലും ഒരു പള്ളിക്കെട്ടാൻ പറ, പിന്നെ ഈ സംഗതി നശിച്ചു പോകും പറ. അതിലും കൂടെ ഗുണം ചെയ്യട്ടെ, പൈസ അതിലും ഗുണം ചെയ്യട്ടെ. അവർക്കെന്നാ അവരൊരു ഷെയർ പാർട്ടിയല്ലേ ഇതിൽ, അവരൊരു ഷെയറിന് പാർട്ടിയല്ലേ ഇതിൽ, അവർക്കെന്നാ വഴിപോക്കനാണ്. ഈ പുള്ളിയുടെ പേര് ചേർത്ത് കഴിഞ്ഞാൽ ഈ പുള്ളിക്ക് ഒരു വാക്കിന് ഒരു വാക്കിന് പുള്ളി എന്ത് പുള്ളി ഇന്ന് പറഞ്ഞതാണ് നാളെ പറഞ്ഞത്. പുള്ളിയുടെ ഒരു വാക്ക് പറഞ്ഞിട്ട്
morning.
Good morning, all of you. Okay, so let's start. So we have, let's start with the engine power. So we know that, the effective power of engine, right? So here, effective power of engine, if you go as per the engine manual, so what effective power they are talking about? They are talking about the brake
Dedicated
power.
horsepower.
No, the brake power of the engine, right? We are talking about the brake power of the engine. So what is the brake power of the engine? That is, say brake power is P. So P is equal to, you know that formula, your, say MEP, say MEP is equal to PE, right? So PE into L into A into N by 60 into number of cylinders, correct? Yes, please.
Yes, sir.
Right? So, this n by 60 is written as small n, right, as a revolution per second. And if you think of L into A is constant, and number of cylinders will also be constant for a given engine, right? So, we can just rewrite this equation as P is equal to C into PE into N. Is that okay? Where C is a constant. Okay.
Yes, sir.
Right? Or
सर ये MEP इक्वल्स टू P क्या लिखा सर स्टेटमेंट छूट गया मेरा तो था एक रिपीट कर
MEP को के लिए symbol use किया है PE, right? PE is the symbol for MEP of the engine, right?
ओके
Okay. So we get this formula. So we can write or P is equal to C into n to the power 1 for constant MEP. Is that okay? ठीक है?
Yes, sir.
सर ये प्लान
So this
में
is-
बाद में नंबर ऑफ सिलेंडर है n by 60
number
into
of-
number of cylinder.
Right. Otherwise, you'll have to calculate for each cylinder and add up, isn't it? But
Okay,
supposing
okay,
the
sir.
units are balanced, then they will produce the same power theoretically, right? Correct.
Yes, sir.
So we get P is equal to C into n to the power 1, right? For constant MEP. Now let's go for the your fixed pitch propeller. So for the fixed pitch propeller or for the FPP, right? So we have what is called a propeller law, right? So this propeller law for the gives the what is the demand power for the propeller, right? So there, as per the propeller law, let the propeller power is equal to PP, right? Propeller power. So what is the formula we have? That is PP is equal to C into NQ, or maybe we can put C1 here, right? So C1 into NQ, or the original thing was propeller power is proportional to cube of the speed. Okay with us? So there is a cubic relationship as well as far as fixed pitch propeller is concerned. So this relationship can vary actually between 2.3 to 3.0, but for FPP, we take the propeller power proportional to cube of the speed. So if we remove the proportionality sign, we get a constant C1. Is that okay?
Yes, sir.
Yes,
Yes, sir.
Is this derived or we have to just assume it?
Yeah, just assumed it because this is experimental, right? So this actually, the propeller power is equal to, is proportional to n to the power k, and k varies between 2.3 to 3.0. Okay? ठीक है ना? but for FPP, we see that it is closer to 3.0.
Okay, sir.
Okay. So this thing, same thing, if we can rewrite as C1 into n to the power I, where I is equal to 3. Okay with that? Yes, please.
Yes, sir.
Yes, sir.
So come back to the previous one. So if we had written here equal to C into n to the power I, so here I was equal to 1. Correct?
Yes, sir.
Right. Next, we had, the power of the engine, that is power is equal to, power of the engine. So that was equal to that PE into L into A into N into number of cylinders, correct? So that was the power of the engine. And for the propeller power, we had proportional to n cube. So these are the two things which we have done, and we expressed each power as P is equal to C into n to the power I, where once I was equal to 1 and the second time I was equal to 3. Correct? Yes or no?
Yes, sir.
So now what we are going to do, we are going to take logarithmic scales. Okay. So if we take logarithmic scales, then P equal to C into n to the power I. If we take log of both sides, so what it becomes, log P is equal to I log n plus log C. Agreed? Yes, please.
Yes, sir.
Right? So if we express it in the standard, form for a linear equation, so what do we have? Y is equal to mx plus c. Remember? So this is how a normal linear straight line is denoted. Y is equal to mx plus c. M is the slope, and c is the y-intercept. Correct? Yes or no?
Yes, sir.
Right? So if now supposing we want to express the same thing here, so how it will look like, right? So when we are saying that this is one line, this is one line, so this is my y-axis and this is my x-axis. So what we are saying is this is the line, right? So this is the line, y is equal to mx plus c, right? Okay, and C, the y-intercept is this. So this is my y-intercept C when we say y equal to mx plus c. And what is m? M is the slope. Okay with that?
Yes, sir.
So everybody okay with this part, right? Yes, please.
Yes, sir.
Yes, sir.
So when we say propeller power is proportional to n cube, and then we take logarithmic scale. So if we take log scales, so what will be the slope? So what will be the slope here?
Three, sir.
Slope is equal to 3, right? And if we take for the engine power, where we said engine power is proportional to n into your engine power, that is power of the engine, is proportional to n into PE, right? And for constant PE, taking logarithmic scale, so how much will be the slope? Slope will be equal to 1. Correct? Okay. So now if we draw these lines, right, taking the logarithmic scale, so how they will look like, right? So this is my y-axis and this is my x-axis, right? And I'm drawing it for logarithmic scale. So this is my I equal to 0. This will be I equal to 1, right? So this will be I equal to 2, and this will be I equal to 3. Is that okay? Where P is equal to n to the power I into C. Is that okay?
Yes, sir.
Yes, sir.
Okay. So then which one is the constant MEP line? For MEP,
I equal to
I
0.
equal
I इक्वल टू 3 x
I equal
इंटरसेप्ट
to
पे क्या आ गया
1,
वो
no?
इंटरसेप्ट पाना है ना
I equals to 1.
I equals to
Yes,
1.
yes, sir.
So that means this line is my constant MEP line. Correct? Okay with that? And what
Yes,
is
sir.
I equal to 3? I equal to 3. This line is
Propeller.
your,
Propeller line.
Constant line for propeller.
so this is my propeller curve. Okay with that?
सर ये I इक्वल टू 3 x इंटरसेप्ट पे क्यों आया ये भी y इंटरसेप्ट पे आएगा ना
क्या चीज I equal to
I इक्वल टू 3 लाइन x इंटरसेप्ट पर आ रहा है क्या
I equal to 3 लाइन x एक्सिस पे आ रहा है क्या? हाँ, क्योंकि स्लोप बढ़ गया ना, ठीक है ना, स्लोप चेंज हो गया ना. I equal to 1 का जो स्लोप था और I equal to 3 का जो स्लोप था, दोनों का स्लोप अलग है ना.
बट ऑल दीस लाइंस y इंटरसेप्ट आएंगे
तो
प्लस
इसका जो इंटरसेप्ट जो आएगा, इंटरसेप्ट इधर आएगा. दिस विल बी द इंटरसेप्ट, राइट? करेक्ट ना?
हाँ माइनस माइनस
सर I equal to 1 कांस्टेंट MEP लाइन कैसे होगा सर? थोड़ा क्लैरिफाई करेंगे.
Okay. So what we said, engine power is equal to, remember that, C into PE into N, correct?
Yes, sir.
And
Yes, sir.
for constant MEP, only when you put constant MEP, the power is equal to C into N. Yes or no?
Yes, sir.
Yes, yes, sir.
इक्वल टू और
And that
प्रोपोर्शनल
is N to the power 1, correct? So when
Yes,
we are
sir.
when we are taking I equal to 1, so that time we are assuming MEP is constant. So the constant MEP lines will be drawn with a slope I equal to 1. The propeller
Okay, okay,
curves
okay,
will be drawn with a slope I equal to 3 when we take logarithmic curves. ठीक है?
Yes, yes, yes.
Right? So if supposing this is my power and this is my speed, and if I had drawn the propeller curve, the propeller curve would have looked like this, because it is P proportional to N cube. So it was a cubic relationship, right? But it is difficult to work with a non-linear scale, right? So what we wanted is a linear scale, and for the purpose of getting a linear scale, what did we do? We took log of
Log
both
scales.
sides, right? And then it became a straight line, correct? Okay with that?
Yes, sir.
Yes, sir.
Yes.
Right?
Yes, sir.
Because we wanted to make it easier and make it a linear scale. So although it says propeller curve, but on the diagram it appears as if it is a linear, it is a straight line. ठीक है ना? Okay so far?
Yes, sir.
Yes.
Yes, sir.
Okay. So next, what we are going for is your layout.
सर ये ऊपर का थोड़ा सा नीचे करेंगे जस्ट फॉर अ सेकंड
Okay.
Sir, when N is equal to 3, it's the propeller curve, no, sir?
When I is equal to I equal
Oh,
to
sorry, I is equal to 3, but so, okay.
correct. ठीक है ना? So what we are going to draw now
और सर ये प्रोपेलर को ये जो कर्व के बाद में लाइन कैसे हुआ सर उसका क्या assumption बोला था आपने
log ले लिया ना, दोनों साइड में log लेने के बाद एक linear relationship मिल गया ना, correct?
यस सर
No?
यस करेक्ट
P is proportional to N cube, but log log P is proportional to 3 log N. So it becomes a linear relationship, right? So then you get a straight line. Correct?
Okay, sir. Okay, sir.
So now what we are going to draw is the layout curve or the layout diagram, what it is sometimes said. So in this layout curve, we will have some what is called the layout points, right? L1, L2, L3, L4. How L1, L2, L3, L4 are chosen, so that we will see later, right? First, let us move into the layout diagram, right? So in the layout diagram, so what we have on the two sides, so this is my layout diagram. So in this, you have got power as percentage, right? And also the engine speed as percentage, right? So both are expressed in percentage form, right? And you are using logarithmic scale. Okay with that? Okay.
Yes, sir.
Both have been expressed as percentages, and you're going to use logarithmic scale, right? So here what we have got two constant MEP lines, and we have got two constant RPM lines, right? So let us have the two constant MEP lines. You know what angle the MEP lines are drawn, right? So MEP lines are drawn for I equal to 1.
One. One.
1. So we are drawing one constant MEP line like this, and we are having another constant MEP line like this. Okay, one line parallel to another line. So these are the two constant MEP lines. And how the constant RPM lines will look like?
With slope 3, sir.
Vertical,
No,
vertical.
constant RPM
Almost.
will be vertical lines, isn't it?
Right.
Constant
Yes,
RPM
sir.
line
Yes,
will
yes,
be
sir.
vertical lines. So you just have
Yes,
to
sir.
draw vertical lines like this, correct? Okay with that? And then we are putting these points L1, L2, L3, and L4. Fine with that?
Yes, sir. Yes, sir.
Okay. The point L1 corresponds to NMCR. Okay, corresponds to NMCR. So what is NMCR? NMCR is the nominal MCR of the engine. So what do we understand by this term, nominal MCR of the engine? Yes, please.
So means this engine can
Maximum output of the
produce power
engine
this much, not
will be
beyond
running at
this.
this much.
So it
This is
depends
the
upon
maximum power the engine can produce. Correct?
yes, sir.
Right? So if this is the maximum power the engine can produce, then why your installed power of the engine becomes less, right? So the installed power which we write on the nameplate of the engine is which power? That
MCR.
is the SMCR, right?
Okay.
The specified or the service MCR. Correct. So how this SMCR comes into play, right? So we have to understand means how the SMCR becomes less than the NMCR, right? How the SMCR becomes less than the NMCR. So for that, if I draw the same thing, this side is power and this side is speed. And supposing I don't take logarithmic scale. If I don't take logarithmic scale, then this is my propeller curve, correct? P proportional to NQ. Okay with that?
Yes, sir.
And if I superimpose the engine curve over here, So how the engine curve will go like. So this is how the engine curve will be there, right? That is P proportional to M. Okay. Is that fine?
Yes, sir.
Yes, sir.
If I extend this one, this would have probably gone like this, right? And if I extend this one, this would have probably continued like this. So there is an intersection point, right? So this intersection point is there, right? So supposing this intersection point is M1, right? So if supposing I operate the engine at say a particular RPM, say 85%, how much power the engine can produce? This much.
M1.
This is the power the engine can produce. How much power is required by the propeller? This much. Correct? Yes, please.
Yes, sir.
So from here to here, this power is what? This power is the reserve power, right? Correct? So when this reserve power will come into action?
During
Bad weather.
Bad weather, hull fouling.
Bad weather conditions. So, okay, hull fouling, no, right? So we will talk about why not hull fouling, right? Because the propeller curve which we have drawn is called for a fouled hull and propeller, right? The propeller curve which we have drawn is called for a fouled hull and propeller. Anyway, so this reserve power is going to come into action if there is adverse wind, adverse current, if there is a squat effect, right? If there is a narrow channel and all that. So when there is a demand for more power to overcome the additional torque, the engine can supply the additional power. Agreed, everybody?
Yes, sir.
Okay with that?
Yes, sir.
Now at the intersection point M1,
Yes,
so at M1, how much is the reserve power?
Zero, sir.
Zero? Zero. So after M1, what happens? So after M1, if I want to run it at this RPM, right? So this is the power which the engine can produce. And how much is the power demand of the propeller? This is the power demand. So what we get? That the power demand by the propeller is greater than the power produced by the engine. Correct? Yes or no?
Yes, sir. Yes, sir.
So what do we end up after crossing M1?
सर ये किस पॉइंट की बात करी आपने?
Negative reserve power.
As soon as you cross M1, what happens? When you cross M1, the propeller demand power is more than what the engine can give you safely at that given RPM. Yes? Agreed with that?
Yes, sir.
Okay. So what we can say is beyond M1, the engine gets overloaded. Correct?
Yes, sir.
Right? So if we sum up, so everywhere there is reserve power, right? And after the point of intersection of the propeller curve and the engine will get overloaded. So up to what power of the engine you can utilize safely? Maximum what
Below
power of the
M1.
engine you can utilize?
Anywhere below M1.
Right. So up to M1, correct? Yes?
Yes.
So M1 will be your SMCR. Okay with that?
Okay, sir.
Right? But the engine, supposing if I did not have to match this engine with this particular propeller, if I had chosen a different propeller, right? So supposing if I had chosen a propeller with a smaller diameter, right, and pitch, then probably the propeller curve would have gone like this. So if it had gone like this, then I would have been able to utilize the engine power up to this point, M2, correct?
Yes, sir.
So what is determining the useful engine power? The intersection
Propeller
points
curve.
of the engine curve
Okay, sir.
and the propeller curve, correct? And beyond that, the engine power is not usable safely, or at least what we are doing is overloading the engine. Overloading is also allowed. We will see overloading is allowed for 1 hour in 12 hours for electronic engines, and for conventional engines, 1 hour in 24 hours. We can do even 10%. We can go even 10% uh, power above the essence. Okay, so that overload is allowed. But what we can say is up to M1, it is useful. But although the engine was capable of developing more power. Okay with that? Yes, please.
So what limit you said about that overload condition? Please come again.
Overload means what we can say is you
No.
can
I'm
run
asking
the
the
engine
time. I'm asking the time. What you said.
110% MCR for 1 hour in 12 hours for electronic engines, and for 1 hour in 24 hours for conventional engines. Okay with
Okay,
that?
sir. Yes, thank you.
Right. So just look at the same thing here. So when we are looking at the
Sir, one question,
at
sir.
this L1 is the NMCR. So where your point M or the SMCR point should lie, the SMCR point should lie below L1, right? So
Below
your
L1.
power requirement for the engine after it has been matched to the propeller should lie below L1. Agreed?
Sir, one question, please.
Yeah, please.
Sir, during sea trial, are we trying out this overloading condition?
Are we trying out? Yes, we are trying out the overload condition, but not during the sea trial. Where we try out the overload condition? During the shop trial. During the sea trial. During the sea trial, do you have that much
No,
torque?
sir.
No, because the outside weather is good, the hull is clean, so there is hardly any resistance. So as soon as you try to push the rack in, what goes up? The RPM goes up, and you will reach the RPM limit before you reach the power limit.
Yes, sir.
So you will not be able to run the engine at 100% MCR.
Okay, sir.
Correct?
Okay, sir.
Sir, one
So,
question, sir. सर
yeah,
दिस
please.
85% स्पीड का जो आपने ड्रॉ किया है एक्स एक्सिस पे, इज देयर एनी सिग्निफिकेंस फॉर दैट?
No. I just took an example just to show that in part load conditions, we have a reserve power, right? So in all part load conditions, we have a reserve power, but at MCR or the SMCR, the reserve power is 0. You know, the normal question what is asked is why we don't run engine continuously at SMCR. We don't run engine continuously at SMCR, although it is a maximum continuous rating of the engine. Why? Because engine can be run at continuously at SMCR where the outside weather conditions are ideal. But at sea, the operating conditions may suddenly change and you will end up overloading the engine. Correct?
So, okay, the reserve power will not be available, so it will not be safe to run the engine.
Right. So although theoretically, yes, engine is designed to run continuously at SMCR, but you will not try to run it, right? Okay, because what you are setting on the engine is the RPM for the governor, right? And if the adverse conditions change, then the racks will be pushed in and it will have to produce more power, right? So can we continue?
Yes, sir.
सर वन क्वेश्चन सर एक बार वो बताएंगे L3 से L4 ये हाउ इज दिस कमिंग एज अ स्ट्रेट लाइन सर बिकॉज देयर इज नो कांस्टेंट
L3, L4 or L1, L3 is constant MEP line.
Yes, sir. L1 to L3 is constant MEP line. Yes.
L1, L3 is constant MEP, L2, L4 is constant MEP, right? This is constant RPM, right? So this is constant RPM line. Same RPM, no? Vertically upward.
Okay. Okay, the same RPM, yes.
ठीक ना?
Yes, sir.
Okay with that? Right.
Okay.
So next, what we are going to draw in this. So in this, what we are going to do is we are going to now superimpose the propeller curve, right? So the propeller curve, what we are going to do here, we are going to actually draw two propeller curves. So why we are going to draw two propeller curves, so that we'll talk about. But first, let us draw the two propeller curves, right? So first one, this is just one propeller curve. Okay, so this is one propeller curve. So this is say number 2, and we are drawing another propeller curve parallel to this, right? And this propeller curve is your number 6. Okay with that?
Sir, these curves are the logarithmic curves, matlab, na, sir?
All are logarithmic. The whole diagram is drawn to logarithmic scale. Okay, na? The whole diagram itself has been drawn to logarithmic scale. Fine with that?
Yes.
Yes, please.
Yes, sir.
Yes, sir.
Yes, sir.
So now understand that we do what is called the tin test, right? So we do a tin test or a model test of the vessel, where we tow a model of the vessel in the yard, right, in long tanks, in experimental tank test, what we do. And in this, the assumption when we are doing the model test is optimum operating conditions, right? And that is a clean hull and good weather. Okay. So basis this tin test, what is the purpose of this model test or tin test? Is to find, the purpose is to find the corresponding speed and power for propeller design point, PD, right? So the idea is to find the corresponding speed power for the propeller design point. Okay with this? So what we do is we do a model in the in large tanks in the yard, right? And I'm not going into that calculation now, so we'll do that calculation later when we talk about all those various types of coefficients like fuel coefficient, admiralty coefficient, Froude's formula, right? So those things we'll talk about at a later stage, not right now. Right now, what we need to understand is that there is a tank test, and in the tank test, we find what is the power required to tow the model and what speed the model moves, right? We also do the attach a small propeller to the model and see what RPM the model would move if sorry, what speed the model will move if the propeller rotates at a particular RPM. We do the model test without any appendages, that is without any fin stabilizers or something, and then we make correction for those. So there are many details associated with that, but that we will cover up anyway. But just understand that basis the tin test or the model test, where we make a light model and we make it generally of tin. So that is by the name tin test. So what we have got is the power and the speed, right? So we have got the power and the
So what is that PD, sir, which you wrote there? Diagram point PD.
propeller design point, right? So let us see where is this propeller design point. So what we get is the power and the speed, right? So let us see what is this power and the speed and where we are going to put the propeller design point, right? So this was the our mm, propeller curve which we had. So on this we are going to locate that point PD. And where that point PD will lie, the PD will lie on the light running propeller curve. So this is my point PD or the propeller design point. Okay, so this is my point PD or the propeller design point. Okay with that? Right? So how we got this propeller design point without going into the full details, just understand that we needed two things. One was the power and another was the speed. And this power and speed were determined with the help of the model test. Okay with that?
Yes, sir.
Yes, sir.
Yes, sir.
Right? All right. Now what we have to understand that we have drawn two propeller curves, line number 2 as well as line 6. So let us talk about the difference between line 2 and line 6. So the line 2, right, is propeller curve for fouled hull and heavy weather. So that is what is called heavy running propeller. So that is called heavy running propeller. Okay. So that is the line 2 propeller curve for fouled hull. Okay. And heavy weather. So that is called heavy running propeller. And line 6 is your propeller curve for clean hull and calm weather. Clean hull and calm weather. Okay? Is that okay?
Yes, sir.
Now these two will be used for two different purposes. The line number 2 will be used for recommended for engine layout. So line number 2 we will use for engine layout. And line number 6 we will use for your propeller layout. Okay, if you have written this, let us understand this part also, right?
Yes.
Okay with that? So just think that we had these two lines. So we had two lines here, isn't it? So close to each other. So this was line number 2 and this was line number 6. Supposing I supply a constant power, right? So this is the constant power which is being supplied to the propeller. So as long as the hull and propeller are clean, so how much RPM we will get? We will get this RPM N1. But when the hull and propeller gets fouled, so what will happen to the RPM? The power is equal to torque into angular velocity? Yes or no? This
Yes, sir.
equation is fine? Or is equal to torque into 2 pi n, correct? So when the hull and propeller are getting fouled, what is happening to the torque?
Increases.
Right, so torque is increasing. So if P is constant, So what will happen to omega? Omega will
reduce.
Right. So what we have to see is that for the same power, right, if we have a fouling of hull and propeller, the speed will drop to N2. Is that okay? So that means initially my operating point was here, and because of the fouling and of the hull and propeller, we will move towards the left hand side. So from the right, we are going to move towards the left. Agreed with that?
Yes, sir.
Yes.
Right? So every point on the light running propeller curve will be moving towards the left. Correct? When we have a fouling of hull and propeller. Yes or no?
Yes, sir. Yes, sir.
Right? So when you are designing the engine, means when you are determining the engine layout. So for determining engine layout, what we said, which curve we are going to use? We will use curve 2 to be used. Right? So what do we mean by curve 2 to be used? What we intend to say is this was the engine curve, this was the propeller curve, and this is my light running propeller curve. So where I should choose M on basis of which one?
सर अंदर वाले पे
The one
lines.
closer, which has lesser power.
Right. So understand the intersection point or the engine layout has been chosen on the basis of heavy running propeller curve. Right. So what we have to understand is the engine layout chosen on basis of heavy running propeller curve. ठीक है, on basis of heavy running propeller curve. So we have to, have an idea of how much will be the heavy running propeller curve, and there will be a difference in the RPM for heavy running and for light running, right? So how much can be the difference? So that difference is defined at this. Sorry. So that difference between the heavy running and the light running is defined between these 2 points. So at the power corresponding to PD, if the hull and propeller gets fouled, so this will be the drop in RPM, yes or no? Correct?
Yes, sir.
yes sir
Right? So if you go from here to here, what is it? It is heavy running. If you go from here to here, it is light running. Correct?
Yes, sir.
So this way you're going from for heavy running, and this way you're coming at light running, right? So now what we have to define is what is this light running margin. Light running margin corresponds to the the difference in RPM at a power corresponding to PD, right? So what we have to think in case of light running margin as the difference in RPM at a power corresponding to PD. Is that fine? Okay with that?
तो ये क्या बोला आपने रनिंग मार्जिन
Light running margin. Okay with that?
So जब normal engine में when there is a torsion meter installed, right? When you see that when engine running on, it starts up, it shows 6% light running. So what does that indicate?
Right. So yeah. So let's have what is this?
Sir, could you repeat that sentence once again, sir?
You please write it down, so that will be better, right? So compared to the, please write it down and then we can discuss it, right? So whatever I said, to the heavy running engine layout line 2, we recommend, that is your we use, right, light running of 3% to 7% for design of propeller. In other words, the LR margin, that is the light running margin, is how much? 3 to 7%. Okay, so the LR margin is 3 to 7%. So when we said that there is a, that this drop in RPM corresponding to the PD point power. So how much is this drop in RPM? We are talking about is 3 to 7%. Okay with that?
Yes, sir.
Yes, sir.
Right? So tell me, when the vessel is coming out of the dry dock, so close to which line you will be operating?
Sir, line 6.
Line 6.
And at the final leg, before you enter the dry dock, you'll be operating closer to line number 2, right? So what we have to understand is that the operating point will lie somewhere between line number 6 and line number 2, right? More the fouling of hull and propeller, more we will move closer to line number 2, right? Now, as a designer, you have to anticipate how much will be the drop in RPM between two dry docks. Okay, so if you make a fair estimate of how much will be the drop in RPM between two dry docks, so you can increase the engine installed power to overcome that additional torque and make up for the drop in RPM. Yes or no?
Yes, sir.
Right? So if I know that yes, 5% is the maximum drop in RPM, so to overcome that 5% RPM drop, how much additional power of the engine is required? So I can fit an engine of a slightly higher power to overcome that drop in RPM. So this drop has to be anticipated correctly by the yard, right? So that will depend on the profiling of the hull, the trading area of the hull, right? Okay, so and the speed of the vessel. So all that will decide how much will be the fouling of the hull, as well as the quality of the paint which you are going to apply on the hull. So basis of that we have to determine. So it is approximately between 3 to 7%. So what we can say as an average, 5% is the LR margin. Okay. ठीक है?
Yes, sir.
Everybody okay with this so far? Can we move on?
Yes, sir.
Yes, sir. Yes.
Right. So what we have got now is that the operating point has shifted, right? So now the operating point has shifted, and now we are going to add two margins to this. So let us draw the figure and then we will discuss what are these two margins, right? So first is we will have one point which is called the SP point, and another point will be called the MP point. So just draw this and then we'll discuss what this SP and MP mean. But you can see that the SP and MP, where they are placed on which curve? On the heavy running
Line 2.
Heavy running curves.
propeller curve, right? So this was the power corresponding to PD, correct? This is the power corresponding to SP, and this is the power corresponding to MP. So if we see from here to here, there is an increase in power. From here to here also, there is an increase in power. So the first one, that is the difference in power corresponding to PD and the SP point. So this is called the C margin. Sorry, this is called the C margin. Okay, and this is 15% of PD. Okay, so just write this. This is C margin, 15% of PD. And the upper one, the higher one, this was called the engine margin.
Engine margin.
And this, the relationship is SP is equal to 90% of MP. Okay. Yes, please.
Sir, can you please repeat this one? I just missed it. SP and MP, shaft power basically.
No, I have not explained what is SP and MP. I've just
Okay.
One is SP and another is MP. So we have to actually talk about what is SP, what is MP, and why these power margins are provided. But if we look at the figure, the power corresponding to SP and the power corresponding to PD, there is a difference, and that is called the C margin. And the power corresponding to SP and MP, there is a difference, which is called the engine margin.
Engine margin.
Okay.
All right.
Right.
15% of PD is propeller design, right?
Design point. So design point के हिसाब से supposing this power is X, right? So corresponding to SP, how much it is? 1.15x, correct? Okay with that?
Yes, sir.
So okay with this? Can we proceed, everybody?
Yes, sir.
Okay.
Sir, C margin थोड़ा बता दीजिए. What is C margin and all?
What is C margin? What is engine margin? That we have to talk about, right? So we have not discussed that part, right? So I just wanted to introduce that C margin and engine margin, right? So
सर ये line 2 पे ही था ना?
Line number 2 पे ही था, right? So we had
yes,
this.
Sir. Yes, sir. Thank you, sir.
So we had this line number 2 and we had this line number 6, correct? And we had this point PD here, and then we moved like this and reached a point here. And now we are saying that move up to a point SP here and move up to a point MP here, correct? That is what we were saying? Yes or no?
Yes, sir.
Yes, sir. Yes, sir.
So in other words, go up like this, right? And when you come to MP, we want to say that MP is your MCR point or the SMCR, right? So how do we come to this? So let's discuss that part, right? So now what we have to discuss is why we need C margin and why we need engine margin, right? So first thing is start with the C margin. Okay. So what we have to think of, that there will be fouling of hull and propeller, right? At the same time, weather may go bad. Both can happen at the same time.
Yes, sir.
Yes or no? Right? So in other words, you have fouled hull and propeller, and at the same time you have adverse wind and current. Correct?
Yes, sir.
Now, if this is the condition, right? So I take this as the, let us take this as the condition. So vessel fully loaded up to your summer load line, right? Vessel is fully loaded up to summer load line. and we have a fouled hull and propeller, and we have adverse wind and current. Still, vessel should meet the required service speed. Yes or no? If it doesn't meet the required service speed, will it be viable in the market?
No, sir.
No. No, sir.
No. So if we had an ideal condition where there was no adverse wind and current, and if there was no fouling of hull and propeller, then how much should have been the installed power of the engine? The power corresponding to
PD.
or corresponding to PD would have been good enough. But in the actual scenario, we will have fouling of hull and propeller, and we will have adverse wind and current. So we will require to overcome this. So all this is what it is doing. We know power is equal to torque into angular velocity. Now which one we want to keep constant? We want to keep omega constant. So if you want to keep omega constant, when the torque is increasing, what you have to increase?
Power.
The power must increase. Right? So if the power has to increase, you have to put an extra power margin. Correct? Yes, please.
Yes, sir.
Yes, sir.
So this extra power margin for overcoming the adverse wind and current and for taking care of the fouled hull and propeller. So that is traditionally, I'm writing the word traditionally because it can vary, right? So traditionally about 15% of PD. Okay with that? So traditionally about, yeah, please.
But sir, for fouled hull and propeller, light margin has already been given, no?
Light margin is what? Light margin is for the drop in RPM. But to overcome the drop in RPM, what you have to do? You have to generate a power margin, isn't it? जो light running margin है, LR margin है, what is that? That is the drop in anticipated drop in RPM, right? But what you need? Do you want the RPM to drop? No. So you have to put additional power to overcome that drop in RPM. Plus you require additional power to overcome adverse wind and current. Okay with that? Yes, please.
Yes, sir.
Sir, when you
come again.
When you say adverse wind current, is there any specific limit?
Cannot hear. Please one by one.
When you say adverse current, is there any specific limit for that, for the wind speed and some?
Specific limit means, yes. See, now as we said, so we have to again anticipate when we say BF4 or something, right? Above BF4 is, bad weather and all that. So that is again a requirement of the owner. So you can always have a higher margin. In other words, the heavy running propeller can be placed, heavy running propeller curve can be placed further to the left of the light running propeller curve. So you can see the difference, 3 to 7%. So somebody can choose 3%, somebody can choose 7%, somebody can even choose 10%. So the owner who chooses 10% as a margin, so his engine will be more powerful, right? So he will be able to overcome more adverse wind and current. But why he will not go for very large power margin? Any reason for that?
EEDA.
EEDA. Because जितना power आप install करोगे उतना उसका 75% पे आपको चलाना है, right? So irrespective of whether you require that power in operational phase or not. So that is why from the design point of view, you are being taxed if you put a too high an installed power of the engine. So that is why you will try to meet the requirements that the vessel is safe, vessel is still viable in the market, vessel is able to overcome your wind and current. You have to see that as per the charter party, standard charter party contracts are already there, where it says that if the wind force is above this, If the swell height is above this, chatter party terms will not be applicable. So till the time it is applicable means you have to meet the requirements, correct? Beyond that, where it is not applicable, nobody is asking you, right? So vessel speed can drop, consumption can increase, right? You are not answerable. ठीक है ना? Okay with that?
Yes.
सर मैं पूछ रहा था ये 15% ऑफ प्रोपेलर डिजाइन है करेक्ट?
Yeah, PD point के corresponding जो power है, add 15% above that, right? So अगर मान लो PD point में है 20,000 kilowatt, so 20,000 plus 15% of 20,000, correct?
Understood.
Right. So we have now got the SP point, right? So this point SP corresponds to NCR. And what is the NCR? Normal continuous rating, right? That is the NCR. So SP point corresponds to NCR, the normal continuous rating. So if you install an engine as powerful as SP, you can overcome adverse wind and current, you can overcome falling of hull and propeller and be able to move the vessel at the required service speed, vessel fully loaded up to the summer load line, right? So this should serve our purpose. So SP, as we can see, is corresponding to NCR. Which is the contractual power? Contractual power is NCR or MCR?
MCR.
Right, so contractual power is MCR, and you know MCR and NCR, what is the relationship? So this is your contractual power, and you know your NCR is equal to 85 to 90% of MCR. In other words, although NCR would have served all the purpose, you are still going for an additional margin. So this margin which you generate is called the engine margin. Okay, and taking the engine margin into account, you get the specified MCR point, which is your MP. Okay with that? Yes, please.
Sir, could you please repeat, sir, this last statement?
What I'm saying is the MP corresponds to MCR of the engine. SP corresponds to NCR, MP corresponds to MCR. So the difference between your MCR and NCR, that margin is called the engine margin. Okay with that?
Okay, sir. Okay.
Right? So why do we need the engine margin? So purpose of engine margin. So why do we need the engine margin? The first and most important point is aging of the engine, right? So as the engine becomes old, as its components wear and tear, it will not be able to produce the same amount of power. So if it cannot produce the same amount of power, now your vessel will fall below the required service speed. So if you have additional power over and above SP, you can still run the vessel at the required service speed. Say after 5 years, 10 years, 15 years, the vessel will still be able to do the required service speed. Okay with that?
Yes, sir.
Yes, sir.
Second is your acceleration, right, of engine. So supposing you want to increase from 80% RPM to 90% RPM. If you have more reserve power, will the response be better or not?
Yes, sir.
Right? So the response will be better if you have more reserve power, right? So the acceleration of the engine will be fast. You will be able to reach the new set point earlier. But if the margin was less, the engine would have been hard to accelerate. Okay with that?
Yes, sir.
Third is the from the SFOC
Yes, sir.
point of view. So if you take from the SFOC point of view, you remember we drew it last time also, SFOC and percentage MCR load. So this is how the curve is going, right? So if you are running at 90% MCR, that is your NCR, this is my SFOC, right? And if I run it at 100%, this is my SFOC. So there is a saving in SFOC, yes or no? If you run it at NCR instead of MCR, is that correct?
Yes, sir.
You can, if you have additional power, you can use in emergency, say piracy attack or something, you can increase the speed of the vessel over and above the service speed. Yes? Correct?
Yes, sir.
If you are on time charter, right, and if you are falling behind the schedule, you can accelerate the vessel further. You can go beyond the service speed if you have reserve power. Okay.
Yes.
Is that fine?
Yes, sir.
So everybody okay with this?
Yes, sir.
Yes, sir.
Sir,
Okay.
sir, could you please explain what is a contractual power, sir?
Contractual power is the, see, there is a contract which is signed between the engine maker, say MAN, and the ship owner regarding what is the power of the engine, what should be the installed power of the engine. So that is the contractual power. And corresponding to the contractual power, there will be a contractual SFOC. So he has to prove the contractual power and the contractual SFOC during the shop trial. The maker has to prove. Okay. At the same time, he has to also prove the minimum SFOC and at what percentage MCR power it occurs. Okay with that?
Okay.
सर फिफ्थ पॉइंट क्या बताया सर आपने टर्बो चार्जर वाला
Time charter.
Time charter.
Okay.
Sorry, it's my bad.
If you're falling behind the schedule, then you can accelerate if you have reserve power. Okay.
Someone's question, sir.
For dry dock also we can reach on time interval.
Dry dock we can reach on time. No, dry dock, what you have to anticipate is that how much should be the LR margin, right? If you have not anticipated the LR margin correctly, then what will happen? Your vessel speed will drop before you reach the dry dock, and then you will have to do underwater polishing of the hull and propeller, right? So which you don't want to do unless you have long anchorages. So you must anticipate so that the vessel is still viable in the market even in the last run before the dry dock, right?
Someone's question, sir.
Okay. Yes, please.
Sir, my question is, sir, if now we are late, time charter, we had some rough weather and all that, and after that rough weather crossing, we have...
Accelerate, obviously your consumption will increase, right? So you will have to see what can be done about the consumption. It is like a double-edged sword, right? If you man to match the time, you will be in penalty for the consumption. If you want to match the consumption, you may be in penalty for the time. So that is an informed decision which you have to take, right? But if the company does decide that where the penalty will be less, and if you do want to make up the time, you can only make up if you have more power, correct? Okay with that?
Yes, sir. Yes, sir.
सर आपने वो डायग्राम में एक जगह लिखा हुआ था engine margin is normally 90% of NCR लिखा था क्या सर?
यही part
which is equals to 90%.
वो
10 to 15% हो जाएगा ना सर?
90% of MP ऐसा लिखा होगा शायद, राइट?
आई थिंक वो जो मेन डायग्राम था उसमें बड़ा बड़ा।
हाँ वही SP equal to 90% of MP। हाँ ठीक है ना?
हाँ ये यस यस यस।
So everybody okay with this part? Can we move on?
Yes, sir.
So the installed power of the engine is how much? The installed power of the engine is MP. And where does the MP lie? MP lies below L1. Correct?
And sir, what things we promise in charter party agreement in this, which power and which RPM we promise?
What power and speed we promise? We promise as per NCR, that is as per the SP point, right? So as per the SP point, this is the power, this is the speed, this is the consumption. So whatever we are committing is as per SP. SP to MP is for reserve. Later on, we may have to increase the consumption part because the wear down of the components will take place. But in a new vessel, you are giving figures corresponding to SP. Correct?
So in short,
later on, we have to revise the fuel figures. Yes, please.
So in short, if vessel is new, I'll reach the charter party agreement in NCR only.
I'll make the charter party agreement at.
I mean, if vessel is new, I'll reach the conditions promised to charter in normal complex rating only.
Right. But after the vessel becomes cold, you cannot quote the same power or the same SFOC, can you? So then your SFOC will be higher. So you have to quote a higher fuel consumption, right? Engine will cope up, but the fuel consumption will increase. Correct? ठीक है ना?
Yes, sir.
Okay. Now, we said these are constant MEP lines and all that, right? So that part is okay. Now what we have to understand is, we are drawing, one line here. We are drawing one line here. Sorry. Right. We are drawing two RPM lines here and here, right? So what is the basis of drawing the RPM lines and what is the basis of the MEP lines, right? If you reduce the fuel, obviously the MEP of the engine will reduce, the power produced by the engine reduces, correct? If you reduce the fuel, yes or no? Right? So, question is how you choose L1, L2, L3, L4. So L1 we are quite sure. So L1 how we chose? L1 was your NMCR, right? So no question about L1. What was L1, L3? 100% MEP line corresponding to engine built as per NMCR. Correct? Yes, please.
Yes, sir. So
for all units.
And what about L1, L2? 100% RPM line of engine built as per NMCR. So okay with these two statements? So we have the L1, L3 line, we have the L1, L2 line. Correct?
Yes, sir.
L1 L3 में क्या लिखा? Corresponding to engine.
Corresponding to engine built as per NMCR. ये आपका NMCR पॉइंट था ना, और इसके कॉरेस्पॉन्डिंग 100% MEP लाइन था, राइट? और ये 100% RPM लाइन था, करेक्ट? So what we said is this is my L1, L3 line and this is my L1, L2 line. अब हमको क्या चाहिए? सिर्फ एक L4 मिल जाएगा तो my layout point will be complete. Yes or no?
Yes, sir. Yes, sir.
So how to get this? So this is, so L4 chosen as per convenience. So what is the convenience here? So I'll just take maybe two types of engines, right? So let's take, say, your SMC. I'm just giving an example, right? So 90 SMC engine if we take, right? So in this, your power would be between 100 to 64% and RPM between 100 to 75%. Okay, so that means if this is my 100% line, so this is my 74% line. Correct? Sorry, 75% line. Okay with that?
सर वो क्या लिखा है chosen as per
convenience? This all we have to
Okay,
do
sir.
is all our design points and all our calculations should ideally lie within this particular parallelogram which we make after plotting the layout points L1, L2, L3, L4. So line L1, L3 is well defined, line L1, L2 is well defined. Now how to choose what should be the minimum RPM or what should be the minimum power for drawing this particular diagram. So that has to be chosen as per convenience and will vary for different types of engines or different series of engines, right? If it was a K98 MC engine, then it would be 100 to 80% power and 100 to 90% speed. So what we have to understand is that these margins, these lines may vary slightly, right? So these are approximate figures which you can just quote in case asked. Okay, okay with that?
Yes, sir. So in power, this 100% is that NMCR line, no, sir? NMCR line?
Correct.
Okay, sir.
Right? So everybody okay with this, right?
Yes, sir.
Yes, sir.
Okay. Now one last thing I would like to add up to that particular diagram, right? So come back again to that diagram. So in that, so this is our diagram. So in this, we are going to use add up our constant alpha lines, right? So now what we are going to add up is the alpha lines. Okay, so these are constant alpha lines, right? So alpha equal to 0.15, alpha equal to 0.20, alpha equal to 0.30. So these are your constant alpha lines. So let us understand what are constant alpha lines. Unless we understand constant alpha lines, we will not be able to choose the propeller. ठीक है?
ये सिलेक्शन आपने L1, L2, L3, L4 बता दिया, मेरा सिग्नल चला गया था।
L1 बोले, L1 is the NMCR point, इसलिए L1, L3 will be the constant MEP line of an 100% MEP line of an engine designed as per NMCR. Similarly, L1, L2 will be 100% RPM line of an engine designed as per NMCR. Okay with that?
Yes, sir. Sir, और ये जो L2, L4 वाली जो लाइन है वो minimum?
Oh, that is chosen as per convenience, will depend on the configuration of the engine, right? So कितना बोर का इंजन है और क्या उसका configuration है, KMC है, SMC है, electronic engine है. So accordingly, that point will differ. So you can think that L3, L4 can be 80% of the RPM, can be 75% of the RPM, can even be 65% of the RPM. So that line can vary. Okay with that? ठीक है?
यस सर। सर ये L2 L4 वाला भी यही है कॉन्सेप्ट? L2 L4 पूछ रहा हूँ सर, जो मिनिमम एमईपी वाली लाइन जो है वो ऑन की भी जा सकती है ना ड्राइंग में, ये पूछ रहा हूँ सर।
कौन सा? हाँ जा
L2
सकती है,
L4
बट हमको क्या, हमको तो डिजाइन करना है ना, मतलब आपका जो आप कह रहे हो कि एमईपी उसके नीचे जा सकती है कि नहीं,
मतलब सर
right?
इसको जब
नहीं
बड़े
कह रहे
उसमें
हो?
डी रेटिंग वाले ड्राइंग में देखते हैं तो ये खाली एक ऊपर बना रहता है, ये जो लेआउट डायग्राम है, बाकी पूरा प्रॉपर कर्व नीचे से जा रहा होता है जीरो से। तो उस समय अगर हम लाइन इफ वी स्टार्ट ड्राइंग पैरेलल लाइन,
बिल्कुल, अगर हम यहाँ पे पॉइंट ले लें, अगर हम यहाँ पे पॉइंट ले लें, यहाँ पे एमईपी कम है, करेक्ट? हाँ, वैसे ही हमारा L2 इसके इधर भी हमारा, मान लो अगर हमारा कर्व ऐसा बना होता तो यहाँ पे भी इंजन चल रहा होता, राइट? So what we have to understand is we have chosen a particular layout for convenience sake so that our design points lie within that. हमारा PD, हमारा SP, MP सब कुछ इसके अंदर रहे, and we can work for calculating the power of the engine to be installed. But the operating point when you are running in part load conditions can be less also. But part load के लिए तो हम ये नहीं कर रहे हैं. What we are doing here is to find what is the maximum power of the engine to be fitted. Correct?
Okay, okay.
तो अल्फा समझा दीजिए एक बार और.
Come again, अल्फा समझा दीजिए मतलब?
वो ऊपर
अल्फा समझा है. अल्फा तो खाली बनाया, एक लाइन बनाया, राइट? ये कांस्टेंट अल्फा लाइंस क्या है इसको जानने के बाद then only we can choose the propeller. Means we'll be able to choose the diameter and the speed. Okay, only after we know the alpha lines. Okay, can we proceed?
Yes, sir.
Yes, sir.
Yes, sir.
So these constant alpha lines are always shown on the top of the figure, as you can see there, right? And right. So what these constant alpha lines indicate? Okay, so they constant ship speed lines. Okay, so these are called constant ship speed lines or alpha lines, right? So that should be the heading, right? So what do these indicate, right? So they indicate the power required at various propeller speeds in order to keep the ship speed constant. Just write this, then we can discuss it, right? So they indicate the power required at various propeller speeds in order to keep the ship speed constant. निकलिए?
Yes, sir. Yes, sir.
Yes, sir.
It is assumed that for each ship speed, the optimum propeller dia is used. Okay, the optimum propeller diameter is used. So understand, what is engine distance? We are done slip, isn't it? So what was the engine distance?
pitch into RPM कर देंगे.
Total number of revolutions into pitch. Is that okay?
Yes.
Yes, sir.
Yes, sir.
So that means if a pitch of a propeller is higher, if it makes less number of revolutions, the vessel speed will be the same?
Yes, sir.
If I correspondingly match the RPM and the pitch, I can still achieve the same vessel speed?
Yes, sir.
Yes,
correct?
we can.
Right. But what is the challenge? The power will not be the same. The power required will not be the same. So power will vary, but there will be various combinations of RPM and pitch which can give us the same product or the same result. Agreed with that?
Yes, sir.
So now what we are going to go for, come again?
What is written in the blue line after that each ship is speed?
It is assumed for each ship speed, the optimum propeller diameter is used. The optimum propeller diameter is used. Right? So now we have to understand, so what is this, how this, so if we say alpha, supposing if we take alpha is equal to, I'm just taking an example, say alpha is equal to 0.28. So this is my alpha, supposing. Alpha can be anywhere between 0.15 to 0.30 as we could say in the diagram, right? But supposing we take alpha equal to 0.28 and let us draw the 0.28 alpha line, okay? So I'm only drawing the 0.28 alpha line. So this side is the shaft power, okay, and this side is your propeller speed, okay, shaft power and propeller speed. Okay with that?
Yes, sir.
All right. So now just draw these lines and then we can discuss this, right? So this is the D line, right? So says this is 6.6 meters, 6.8 meter, 7 meter, 7.2 meter. Okay.
What is this, sir? What is this line, sir?
D line, right? So how this D line has been drawn, so we'll talk about. So D. So just draw this D line first, right?
Okay, sir.
So, right, and corresponding to 7.2, just draw the P by D line, right? So this is my, sorry. So this is my 7.2, and this line which we have constructed is the P by D line. So we have a D line and we have a P by D line. Okay, done so far?
Yes, sir.
Yes, please.
Yes, sir.
So I'm just reducing it. So now understand, D is the dia of propeller, P by D is the pitch to diameter ratio. ठीक है, P by D is the pitch to diameter ratio. Okay?
Yes, sir.
So if I choose a diameter of propeller as 7.2, supposing 7.2 is the diameter of the propeller, as you can see in the diagram. So at this point, supposing the P by D ratio is 0.7, this point it is 0.65, this is a 0.6, and so on, right? 0.55, and this side is 0.85, 0.95, 1.0. Okay, so this is the pitch to dia ratio. If the pitch to dia ratio is more, so in one revolution it will make a larger distance. Agreed?
Yes, sir.
Yes or no? Right?
Yes, sir. Yes.
Now, okay. Now come back to this particular diagram. So what we said is this is for a constant alpha equal to 0.28. So alpha is constant, right? And so the vessel speed will be constant in our case. So that alpha equal to constant and vessel speed is constant is corresponding to the D line. So this D line is the line which is corresponding to that alpha equal to 0.28. So if I want to keep the vessel speed constant, and if I choose a propeller diameter of 6.6, what should be the power and what should be the speed? So if you see, if I choose 6.6 as the dia, so this is the power and this is the speed. Correct? Okay with that?
Yes, sir.
अरे 6.6 अपने आप सेलेक्ट करा है
Vessel speed. Come again?
6.6 वैल्यू अभी ऐसी आर्बिट्री वैल्यू लिया आपने समझाने के लिए
लिया आपको देखना पड़ेगा कि आपके आफ्ट में कितना जगह है, means what is the largest size of propeller you can fit, and at the same time you should have that much tip clearance that you don't have aft end vibration, right? So taking that into account, supposing if I put 6.6, then what is the power required by the propeller? P1, and what is the RPM it should be running? N1. Then I will get the required service speed. Supposing if I decide to put a diameter of propeller equal to 7.2, so how much will be the power required? P2. And how much will be the speed at which the propeller has to move? N2. Is that okay?
Yes, sir.
Vessel speed, same. So what do we see? That for the same vessel speed, increasing the diameter of the propeller, what happens? The power required reduces, correct? Yes or no?
Sir, just one small doubt, sir. So this D line is for that particular alpha or what, sir? For particular alpha value?
For that particular alpha, correct. For that particular alpha equal to 0.8. When we said at alpha, what we said is vessel speed will remain constant. There will be a combination of what? Diameter and pitch of the propeller,
Pitches.
and we will
Okay.
and RPM. So there will be a combination of RPM, diameter, pitch of the propeller, keeping vessel speed constant, where we will get the same result. But the power requirement, what we said, for constant alpha, the power requirement will not be the same. Correct?
Okay.
Yes or no?
So for this whole graph, the ship speed will be
When we
constant.
do the power against speed, what we said, this is our alpha line, correct? Yes or no?
Yes, sir. Yes.
So if this is the power, this is the speed, RPM. If
Okay, sir.
this is the power, this is the RPM. But is the vessel speed changing?
No, sir. Vessel speed. Yes.
Constant.
So if I take alpha equal to 0.28, so at this, the vessel speed is constant. So V is constant. N is changing. V is changing, right? And what we said, diameter and pitch is optimum. Correct?
Yes.
Yes or no?
सर पर वो ग्रीन और पर्पल का तो लाइन अलग हो गया ना, पावर का तो 2 पॉइंट बन गया ना,
पावर का 2 पॉइंट बन गया. So P is changing, power is changing. Correct?
and N is also changing.
N is also changing.
Okay, sir.
The speed at which the propeller has to turn is changing for the required service speed. The power that propeller requires is also changing, but vessel speed is kept constant. How you are able to do it? By changing the diameter and pitch of the propeller. Agreed with that?
हाँ सर, सो इसके पहले वाले डायग्राम में ऐसा लिख सकते हैं क्या सर, D equals to alpha and alpha equals to 0.28 for the moment.
E equal to alpha जो लिख रहे हैं वो कब लिख रहे हैं, that is what we have to understand. So far is this part okay? Instead of 6.6, if I choose 7.2, my power requirement for the propeller reduces. Propeller will be turning at a lesser speed, that is lesser RPM, but the vessel speed in knots is still constant. Agreed?
Yes, sir.
Yes, sir.
Right? So it is advantageous to go for a larger diameter propeller, क्योंकि propeller का अगर demand power कम हो जाए तो engine का installed power हम कम कर सकते हैं. Yes.
Normally tip
now supposing normally tip clearance
कितना रहता है सर?
See, that will depend on means you should not have aft end vibration. So about 0.3, 0.25, right, would be the tip clearance, approximate values. ठीक है ना? Okay. So what we were trying to say here. So if the diameter is 7.2 and P by D is 0.7, then how much is the power required? P2. Now supposing somebody puts a diameter of propeller 7.2, but he changes the P by D ratio to 0.65, then what happens? He changes the P by D ratio to 0.65. So then what is the power required? And what is the RPM?
Increase. More power, little more power will be required.
There is a penalty on the power? Yes?
Yes, sir. So dia is same, sir, in this case? Dia is 7.2 only?
Dia is 7.2 only. But somebody changes the pitch. The propeller will have to run at a slightly higher RPM and there is a penalty on power. So minimum power कहाँ पे हो रहा है? For 7.2 diameter, where is the minimum power? When you choose P by D ratio as
0.7.
0.7. 0.7. So 0.7 is called the optimum P by D ratio. Is that okay?
So this graph is by experiment, is it?
This graph is by experiment, right? So this is given by the propeller maker. ठीक है ना?
Okay, sir.
So now you can see 7.2, 0.7 is the optimum P by D. Similarly, मैं 7.0 का भी ग्राफ बनाता, 6.9 का भी बनता, 6.6 का भी बनता. इन सब का ये वाले जो points है, what are these points? These are their optimum P by D points. So the line D which was drawn was joining propeller of different diameters for their optimum P by D. Is that okay?
Sir, repeat करिए last line, sir.
The line D which was drawn for different diameter of propeller, but joining their optimum P by D.
Okay, sir.
Is that okay?
Yes, sir.
Right?
Sir.
So if you follow this line, if you continue to follow this line, then it is constant alpha. Constant alpha equal to 0.28. But if you shift to here, then alpha is changed. Is that okay?
Okay, sir. Okay.
सर हम ये शिफ्ट कैसे करते हैं सर? इसमें 0.28 सर का स्लोप है, क्या है, अल्फा की वैल्यू कुछ रेशियो है, कुछ तो होगा ना अल्फा वर्ड का मतलब सर? ये जो 0.28 वैल्यू है सर, मैं ये पूछ रहा हूँ कहाँ से आई है? कुछ रेशियो है किसी का कुछ?
अच्छा, मतलब किसका कितना होता है? I'll give you a figure of how much it is normally, how much is the
डिफाइन कैसे करोगे? तो हम क्या बताएंगे? कुछ रेशियो है, क्या है? अगर 0.25 होगा तो ये लाइन का स्लोप कैसे चेंज होगा, क्या होगा, वो पूछ रहा हूँ।
अच्छा, ठीक है। So we'll cover that. ठीक है। अभी के लिए almost okay with this? Whatever we have covered? Yes, please.
Yes, sir.
Yes, sir.
Right? So what we have to understand is, for a constant alpha, we can have different diameters and different RPMs and still meet the same what we call the vessel speed. So now I give you a scenario, right, where the installed power.
So when the alpha is changed, means ship's vessel speed is changed, no sir? In that case, when we went to 0.65.
The alpha is changed, the vessel speed is changed. Yeah, correct.
Okay.
Right? Okay. So vessel speed may not change, right? So that is what we will put it. Vessel speed may not change, right? So we'll see that part. But right now, just keep this one. Installed power was your point M, yes? So for the point M, supposing it works out to be 30,000 kilowatt at 100 RPM. Okay, so this should be the power of the engine. ठीक है?
Yes, sir.
Okay.
So point M means MP point, no sir?
Yeah. The MP point, right?
Okay.
So supposing we are trying to put 7.2 dia propeller, because supposing this is the largest diameter propeller which can be put. So how much should be N2 here? And N2 should be 100 RPM, correct? Yes or no? And
Yes,
our P by D should be 0.7. ठीक है ना? So this is what we needed. But unfortunately, we went to the engine maker, and engine maker says that for 30,000 kilowatt, you will require a 7-cylinder engine, and it will run at 110 RPM, will not run at 100 RPM. So now what to do? If it cannot run at 100 RPM, if it has to run at 110 RPM, so now what is the option? So instead of 100, I take 110 RPM. So this is my 110 RPM. So this is my new propeller. New propeller design point. So where the P by D ratio is 0.69. Okay, and there is a small, very fine power penalty. Is that okay? So we will not design the propeller for 0.7. We will design the propeller for 0.69 with a small power penalty.
सर ये एक बार सर फिर से रिपीट करिए, ये क्यों किया ऐसा आपने? 100 से 110 पे क्यों है?
देखो, हम तो चाहते थे कि प्रोपेलर 100 पे चलेगा, राइट? अगर प्रोपेलर 100 पे चलता तो हमारा 7.2 सबसे बड़ा डायमीटर वहां बैठता था और उसका P by D 0.7 होता. So everything would have been ideal. बट इंजन मेकर बोलता है कि इस कॉन्फ़िगरेशन के लिए इंजन विल रन एट 110. अगर इंजन 110 पे चलेगा तो प्रोपेलर इज डायरेक्टली कपल्ड टू द इंजन. So propeller will also run at 110. So then I must optimize the propeller for 110. I cannot optimize the propeller for 100. So that's why I'm changing the P by D ratio as per 110, keeping the diameter of the propeller same as 7.2. Okay. So this is done. So everybody okay with it? Now I'll just answer his part, whatever he had asked. So the relationship, so what we have to see is, we said your P2 by P1, right? So just write down P2 by P1 is equal to N2 by N1 to the power alpha. Okay. So when we said constant alpha lines, in constant alpha lines, what is changing? The speed is changing, the power, the RPM is changing, the
Yes, sir.
RPM, that
But
is
actual
N
RPM
will
is same.
change, P will change, and vessel speed is constant. So what is the relationship between N and P? That is given by this equation. P2 by P1 is equal to N2 by N1 to the power alpha. Okay with that? Yes, please.
Yes, sir.
Okay. So yeah. So how much is the alpha? Approximately, why we are taking this value? So what we have to understand is, this is as per the type of the vessel. So for general cargo, for bulk, for tankers, alpha lies between 0.25 to 0.30, right? For reefers, containers, alpha lies between 0.15 to 0.25. I hope now it is okay, right? This part is clear. Okay. Yes, please.
Yes, sir.
Okay, so we have finished a major part of it, and second time we will take up the other part, that is regarding your limits, right? So when we come to the load diagram. So next time we'll take up the load diagram, please.